In this video, I want to apply some of the basic principles that we've seen, namely chemical class, to understand a little bit about the behavior of some of the hormones. And since I've already done GnRH, I'll move on to the next hormone from the hypothalamus as my example. So I'll title this in a second, but let's begin with the hypothalamus, which is going to be connected to the pituitary through the pituitary stalk or the infundibulum. And if I have my flat pig, FSH and LH, the gonadotropes, are controlled by that GnRH. Flat A, ACTH. Now, what in the world controls ACTH? My next hormone from the hypothalamus must be CRH. So let's see how CRH and my understanding of its chemical class helps me understand its function. Okay, now another name for CRH, if I'm going through my laundry list of the progression of a hormone, the name of the hormone is corticotropic releasing hormone. It's a releasing or inhibiting hormone in its name, so I know that it comes from that hypothalamus. So I know the name and the organ that produces it, hypothalamus. And the name of the cell that will produce CRH is going to just be corticotropic releasing hormone producing cells of the hypothalamus. We're going to name them after what they make. Now, I know the name, the organ that makes it, the specific cell that makes it. Now, the pressing question is how are the cells making this? And to answer that question, we first need to identify the chemical class. And I know that this one is an amino acid based hormone. If it's peptide or protein, I'm not overly concerned about that. Those are made from amino acids as well. I'm not concerned about the length so much. You can get into those nitty-gritty details if you go into endocrinology. But it's an amino acid based hormone. And I'm going to make a video of how amino acid based hormones are made by cells. But essentially we have a gene that codes for CRH. And when we transcribe that gene, we form messenger RNA. And messenger RNA leaves the nucleus and is the directions for a ribosome to translate the protein into the pre or pro hormone for CRH. It undergoes a little bit of modification by the Golgi, and then it can be stored within these CRH producing cells of the hypothalamus until it's signaled to be released. So an amino acid based hormone follows the central dogma of biology. Messenger RNA to the protein, and then it's going to undergo some modification. We get that from a gene. That's how it's made. And it can be stored within the cell until it's signaled to be released. Now, that's because it's polar, and it cannot get out of that non-polar lipid bilayer without being translocated to the membrane by a vesicle. But once it does, the hormone's released by those same cells that made it and the same organ that made it. So I have the name, the organ that makes it, the cell that makes it, the chemical class, how that cell makes it. And now, how it travels through the blood. Because amino acid-based hormones are polar hormones, they can get right into that primary capillary plexus and be swept up by the hypothalamic, pituitary, or hypophyseal portal system. Then those hormones will leak out of the secondary capillary plexus to affect cells of the anterior pituitary. So I know the organ that it affects and that it does not need a protein carrier to get through the blood. Or be moved by the blood. The target organ is the anterior pituitary. And what it's going to do is it's going to cause this anterior pituitary to release a hormone of its own. It's going to affect the cells in here to release ACTH, adrenocorticotropic hormone. So it's going to bind to adrenocorticotropic hormone producing cells of the anterior pituitary, causing it to be released. So now I know the target organ and the specific cell and the effect that it has. It increases ACTH levels in the blood. Now let's take it a step further and appreciate the hypothalamic, pituitary, target axis, or the HPT axis, another basic principle, to see what ACTH really does. Now this ACTH is going to travel through the blood to reach, well, adrenocorticotropic hormone. It's going to affect the adrenal cortex. Now the adrenal cortex is part of the adrenal gland on the top of the kidney. So if I have my adrenal gland, it's kind of like a pancake covering this kidney, and I blow it up like a triangle, ACTH is going to affect the 3 layers of the adrenal cortex, or the shell of this adrenal gland. Not the medulla, but 1, 2, 3 layers of the adrenal cortex. It is, after all, in its name. Now, I'm going to warn you of a little exception here. The ACTH affects layer 2 strongly and layer 3, but very little effect on layer 1. Layer 1 produces the mineralocorticoids like aldosterone. Layer 2 produces the glucocorticoids like cortisol. And layer 3 produces the gonatocorticoids. Now, let's focus in on layer 2. That ACTH is going to cause layer 2 to release a hormone, a glucocorticoid called cortisol. So we could almost say that CRH ultimately raises cortisol levels. But what does cortisol do if we're taking it that far and not the immediate action of it to increase ACTH? Cortisol's main effect in the body is to increase blood glucose. I encourage students not to think of this as the stress hormone necessarily, but to think of it as what it does to help us control stress. It mobilizes glucose into our blood so we have energy to get away from a threat. If cortisol increases blood glucose, we could almost say CRH will raise blood glucose, ultimately. So what would hypersecretion of this hormone do? Increase blood glucose levels. What would hyposecretion of this hormone do? Well, hyposecretion of ACTH, hyposecretion of cortisol, low blood glucose. Now, what's going to cause its release in the first place? And this plays into feedback loops. Now, usually, the ultimate result of this hormone is going to feed back to inhibit that hormone. So, high blood glucose is going to feed back and inhibit release of CRH. Now, it turns out that ACTH can also come back and inhibit it, and cortisol levels can come back and inhibit it. But normally we think of the ultimate effect, high blood glucose, as inhibiting it. What's going to stimulate it? Low blood glucose, or low ACTH, or low cortisol will not inhibit the release of CRH, and we'll get some CRH that causes the release of ACTH, that causes the release of some cortisol, that mobilizes our glucose stores. Now, it's also going to get a human to start developing secondary sex characteristics through androgens and the gonatocorticoids. But that is a little bit smaller of an effect than the glucocorticoids, and very little effect. Be careful of that. Very little effect ACTH has on the zona glomerulosa, or layer 1 of the adrenal cortex. So by understanding the chemical class of CRH, I can deduce how cells are making it. I can deduce whether or not it's stored within the cells. I can deduce how it's going to travel in the blood. And I can even deduce where it will bind on the target cell. It binds on the cell surface, on that lipid bilayer, to a second messenger system. Because it's polar, it cannot get through that plasma membrane. So it uses a second messenger system to cause ACTH to release from the anterior pituitary. We can know an enormous amount and answer a lot of these questions by knowing the name, the organ that makes it, the organ it affects, the ultimate effect of that organ, and the chemical class. We can answer 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I must have missed one somewhere, 13, at least 14 questions about CRH. I'll give many, many more examples. But first, how did I know that it was amino acid based? I know that it's amino acid based because it is not a tyrosine derivative. Not a tyrosine derivative. You can watch the chemical class video. Those are epinephrine and norepinephrine, the catecholamines, and the thyroid hormones, T3 and T4. It is not T3 or T4. It is not epinephrine, norepinephrine, the catecholamines. It also is not made in the adrenal cortex, the gonads, ovaries, testes, or the placenta. And since it's not made in those places, with few exceptions, it's not steroid based. It's not a steroid, because only those organs make steroid hormones, with few exceptions we'll learn. It is amino acid based because it's one of the everything else. It's made in the hypothalamus. Hypothalamus is not adrenal cortex, gonads, or placenta. And it is not a tyrosine derivative. Those are made in the adrenal medulla, but they behave like amino acid-based hormones, or a thyroid hormone, T3, T4, which behave like steroid-based. I should have done that in red to be consistent with the other video. It's everything else. Okay, now we know a little bit about CRH. And there is a disorder associated with low production of CRH. You'll learn about that when you learn about cortisol and ACTH, and that's Cushing's disease. Cushing's disease. Now, hypersecretion of cortisol hypersecretion is Cushing's disease. Hypersecretion of CRH or hypersecretion of ACTH or hypersecretion of cortisol is Cushing's disease. Too much. Addison's disease, I believe it's 2Ds. Addison's disease is not enough. These people can't cope with stress and get their blood glucose levels up to respond, to give the cells the energy they need to respond, because they don't have enough CRH or enough ACTH or enough cortisol. In Cushing's, they actually can develop symptoms of too high of blood glucose, diabetes, insulin resistance, even weight gain, and a characteristic hump on the back of their neck, or moon face, because they become so round in the face. And that's because of lipid. The glucose needs to be stored after being elevated in the blood for so long, and they get some weight gain. That's hypersecretion of CRH, hypersecretion of ACTH, or hypersecretion of cortisol. I'll go over feedback mechanisms. I'll go over how amino acid-based hormones are made and how they bind to and affect cells, likewise for steroid-based. But that's an example of how I use chemical class to begin thinking my way through a hormone. Many more examples to come.